My name is Ashok Regmi, and I will be making this presentation on behalf of our team, which consists of Oguzhan, John, and Armando. And my presentation is basically on work that we did together on a small irrigation, farmer-managed irrigation system in Nepal called Pumpa. What we did in this paper of ours was we developed a simple model of rice paddy irrigation and used it to assess the robustness, vulnerability characteristics, and adaptive capabilities of these systems to respond to shocks. So we know that small irrigation systems they face certain constraints. For instance, it can be not every year water is the same in the river that they draw the water from. Then precipitation can occur in different cycles, and the monsoons can come early or they can come late. So these are certain shocks that a small system faces. And we're looking at how a small system adapts to these changes. And the reason why we thought this work was important is because the issues are directly related to food security. In most of in the world, at least 90% of the farms are small farms, and irrigation water to them is supplied in the majority of the cases by at least one third of small community managed or farmer managed irrigation system supply water to these systems. They rely on themselves, and these systems are across Asia, and in Nepal, the contribution of small farm managed irrigation systems to irrigation is 75%. And the need to understand the capacity is important because, food security is directly tied with these systems, and a lot of poor households, families rely on their food on these systems. And again, as I mentioned earlier, we're looking at increased variability in precipitation and water availability that might be caused because of climate change. The questions that we ask is, do farmers actually choose efficient institutional arrangements given the conditions they face? And how sensitive is the yield to variations in the rain and river flow regimes? And to what extent can farmers increase robustness, i.e. reduce the sensitivity of the systems to variations in rain and river flow? So in order to do this, what we do is we try and construct a simple mathematical model that takes into account certain biophysical and institutional variables in order to answer this question. When I talk about the biophysical variables, we're basically talking about water. That would be the main variable that we're talking about, because irrigation system, that translates in. And institutional variables would be basically when when a system draws water, then they need a set of rules that will govern how this water is allocated and distributed amongst the farms. This is the headwork of the Pumpa irrigation system that we looked at. Water is diverted from the river using a diversion structure which consists of rocks and alien wires. The water that is diverted enters the main canal. Which one is the pointer? Yeah, it enters the main canal, and then this is the gate over here. In case there's a flood, then there's close the gate so that the system inside is not flooded. And the water, once it enters the main canal, is conveyed through different canal systems into the fields. Now this is a schematic of the system that we're talking about. It's a relatively small system. It's 70 hectares, the land area is 70 hectares, and there are the members of the water users community is about 140 households. There are one main canal and 3 branches. The main canal is about 3.5 kilometers. Most of the canal is urban canals. In the main canal here, that would be the main canal. Water is diverted from the river, and there's the main canal, and then distributed. The main canal has a lining, it has a single lining of 2 kilometers. The rest of it is it's urban canals. Now, the block diagram on the right, that kind of captures the system, the system that is described in the schematic on the left. The block diagram is basically, I mean, it is a network. It is a network of nodes, 1, 2, 3, 4, and 5, and 6, which are sectors on the left-hand side, and which are controlled by check valves or check gates in this case. And so that would be a simple representation of the system. And we work on the block diagram and input more information to construct a model. Now, what we're looking at is we're looking at rice cultivation. This system has 2 crops. It does rice, and it does rice in the summer, and it does wheat or corn in the winters. We're basically looking at rice. And one of the important inputs to our model would be the demand for water, how much water is required in the first place. So in order to determine that, we need to take a look at the activities that are involved in growing rice. 5 sets of activities there, and then the cycle. I mean, it takes about 4.5 to 5 months from plantation to harvest. And for each of the activities, the water requirement needs are different. The least is required in the late season and during the seed bed preparation, and the maximum is required during the field preparation. And then in the mid-season also requires, it's the same as the previous, but the mid-season is also critical because during that stage the plants are putting on seeds and there's a need for water. And if water is disrupted at that point, I mean, it affects the yields. Now, this is just a presentation of the prior information in a graphical form. And we have the dates in here. Basically, I mean, when is the planting season starts from May 15 and then ends in October 25. And those are the different stages of rice cultivation. Now, this is a little more detailed diagram. Here, what we're trying to do is we're trying to not only determine how much nominal water is required for different stages, but here we give a band. We're saying if water falls below, let's say, here 150, then it affects the productivity of the yield. And if it goes beyond 300, then there's a situation of flooding, and then that might affect productivity as well. So in order to have maximum productivity, we need to remain within this bandwidth, and we generate these bandwidths for different stages. And this is, of course, I mean, the information we use to generate these bandwidths is our conversation with farmers, and we ask them how much water do you require, and they say, well, we require that much. If you don't get that, then what happens? It's that kind of information that we have. Now, the previous was the demand part of it. Now we're looking at the supply side of it as well. And the water regime is as presented here. From the months of June to September, June to October, I mean, there's an increase in the discharge. And the rice planting cycle is also coincides with the monsoon. So, except for the field preparation part, the very first part, the rest of it, there's sufficient water in the fields. But for the first one, there might be a problem. Sometimes there is enough, sometimes there isn't. So that would be the critical part, and we're taking a look at that. But even for the other parts, although there is water in the river, does not necessarily mean that water comes to the field. lot of them might be flooding, the dead works might be washed away, and then it requires a lot of collective action. People have to come together to put it together. And so there's a lot of activities that are required to get water even in other spheres.